Really, I thought I
There's
still had
always
MATLAB.
there's always an excuse. It's always an excuse with you guys. Goodness. All right, it's recording. All right, cool. So homework 5 is due tonight at like 11:59. Please don't wait till 11:58 to start handing it in. Like Gina said, even if like you didn't complete it, get like partial. Don't take the 0 because your grades, some of you are really not on track to passing this course. So every bit counts, from the homeworks to the quizzes and all that stuff. Speaking of which, the quiz 2 is on Tuesday. I'll talk about in a second what it's going to cover. I'm going to talk about the midterm first, all right? And then homework number 6 is also due Tuesday at the start of class, all right? This is where things really start picking up. This is where things start to get a little heavier on you guys. So please make sure you're on top of your stuff. But before I continue, we got to talk about this midterm and how I'm letting you guys, why am I letting you guys do corrections? This is a very high school thing. They don't do this in college, but I have to do it because just the scores were just so low, even with the curve. And yeah, so this is what we're gonna do. For every single point that you got wrong, you can get up to half the points back. Meaning, if you don't do if you don't do the corrections correctly, you don't get the points back. All right. So let me give you an example of like how to get your points back and stuff like that. All right. So I'm looking for 3 things. All right. I'm looking for 3 things, and this is for every single problem. This isn't for like the whole thing. It's for every single problem. So I'm just gonna come up with a fake question. Okay. So let's say like let's say the question was, I don't know, 3 times x plus 2 is equal to 1. And then this was your work. Right? And let's say I took off like -2 for this. Okay. So how do we do corrections? First thing you do is you tell me, what did you do wrong? Right? So that means you need to look through your work and you need to see and catch, what did you do wrong in your work? If it's something small, if it's something big, if you just left it blank, right? Whatever. So so for this one, you would say, I did not distribute 3 correctly. I don't know if you guys even saw that, right? It's supposed to be 6, not 5. I hope you guys know that. Whatever. The second part is the correct work and answer. So yes, you're starting from the beginning of the problem and doing it over, right? So you would do 3 times x plus 2 is equal to 1, and then you do 3x plus 6 is equal to 1, and then is -5, da, 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 da. Right? That's part 2. You need to show me full work, full answer. And then third thing, so the third thing is, what did I learn from doing these corrections? Man, this one, when I do corrections with my high school students, they like to put the same answer for all of these, but I don't want that from you guys. I need you guys to give me something real. Like number 3, like I swear, if I see this, I learned how to do it. That tells me absolutely nothing. You learned nothing from this, and you are not getting your points back for it. You know what I mean? I better not see that. All right. I learned that I need to distribute to all terms. ... Whatever. Anything along that. That's fine. Right. I learned that I can't forget the plus C when integrating. I learned that I need to watch out if I have bounds or not, because if I have bounds, then I shouldn't have a plus C in my final answer, right? I should have an actual amount, right? I learned to plug in theta values for given a polar function to kind of guess what the function is going to look like. That was one of the questions, right? Those are the answers I'm looking for. So yes, part 2 is important. You're going to redo the problem and you need to get the right answer, right? But parts 1 and 3 are just as important. For example, for part 1, if you say, oh God, I swear if I see this, if you say I did it wrong, well, no bleep, right? Like no bleep, Sherlock. Like you got it wrong. I saw that you got it wrong. I marked it wrong. So if you say I did it wrong, I'm not giving you any points back. I'm not even gonna read 2 and 3. Do you guys get what I'm saying? So it's like these are corrections, but like a little bit more adult. I know corrections you guys are probably used to, like you just redo the problem, but I'm asking for a little bit more reflection. The reason why I'm doing this is because I don't want you guys just to dump all the material from the first half of the class out of your brains, right? That's not a good, healthy way to like learn this stuff. I get it. The final, it's not going to cover everything from the beginning, but you guys still need to know how to do the stuff that we covered up until the midterm. So that's why I need you guys to dig a little bit deeper on these corrections, all right? And if I see that any one of these 3 parts are lacking for any question, then I'm not going to give you the points back. Does that make sense? Once again, you have to do this for every single question you got wrong. At the same time, let me be clear. I am not looking for your life story. I personally am not a big reader. I don't like to read. I'll skim. But if you give me like a 1 full page analysis of like your birth and like how your life caused you to end up at this point in time and space, I'm just gonna be like, all right, I don't care. Like, I mean, I guess that's kind of interesting, but like, please make sure it's relevant. All right. Please don't say, well, I was born in a log cabin in 1343 and I blah, 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 blah. And this is why I got it wrong. Like, I don't care about that stuff. Just be short and sweet and to the point. Okay. Do we have any questions on the corrections? So if you got a 26 out of 50, right? That means you lost 24 points. You could bump that up to 30. Hold on, I can do this. 38 out of 50, which is pretty good. That's a 76%, right? So please consider doing these corrections. Oh yeah, and they're due next. How much time should I give you guys? Let's say next week. Next week. I'll create a thing on Canvas. I'll put it under the midterm. It'll be midterm corrections. So 723 at, let's say 350. Can I ask you guys for a favor when submitting these? Can you guys upload? What will be easiest here? Can you guys upload it all in one PDF? Okay, that's not new, but can you also upload your original submission with the corrections right below it? Do you get what I'm saying? So I don't have to like click back and forth between like, windows and stuff to like see like, oh, what did they do? What did they fix? Blah, 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 blah. So please upload your original exam and then the corrections right afterwards.
So John, are you going to give us like our exam with how you like graded it, like what you marked wrong and stuff?
Do you guys not get notified when I grade stuff?
Yeah, I think it does.
I don't
Doesn't
get
give us a
notified.
notification.
I graded them. I graded them last night. I graded them yesterday. The average was, do you guys really want to know what the average was? It wasn't good. Average was a 28%. 28%. But with the curve, it was a 44%. So not much better. So yeah, that's why I'm doing these corrections. And that's why I'm taking 12 minutes out of class to go through this. Do we have any questions on the corrections?
Are the grades we got accounting with the curve?
Okay. So the ones on Canvas are without the curve. The ones in my personal, like I have a separate like spreadsheet that has like computations and stuff on it, and it has the curve. Those are the ones I submit to Dean Brown at the end, not the ones on Canvas. So I think I said in the beginning, the grades on Canvas may not truly reflect your grades, but at the same time, some of you scored so low that like with the curve, it didn't even matter. So yeah, do the corrections, guys. Please do the corrections. I would not skip out on these corrections. I'm giving you guys a chance to bump up your grade, like, like it's kind of like supposed to be like kind of like a saving grace, so please do them.
How do you make like sure it's all in one PDF?
Say that one more time.
make sure it's all in one PDF when you have to take, like, when you have to do the scan.
Okay, so I don't know what scanning app you guys use, but the one I have, it's called Adobe Scan app. You just take multiple pictures at once and it just smushes it into one PDF. If it's a 20-page long PDF, it's a 20-page long PDF, but it's one PDF. Do you get what I'm saying? Please don't submit multiple PDFs because then I have to click through them. They have to refresh and blah, 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 blah. And oh my gosh, some of you submitted the midterm like that too. Like some of you submitted your pages instead of one PDF. Some of you are submitting super zoomed in like work and I can't even zoom out. And like, I have to like, it was really annoying. It's like it's a little mean that some of you still don't know how to upload stuff correctly. Figure it out now. Figure it out now, not later. All right. You're welcome. You're welcome. Thank you for appreciating my kindness.
Thank you so much, man. You the
John.
GOAT, man. The GOAT,
Thank
the
you
best
for the
teacher
chat,
ever,
John.
man. It's crazy, man. I don't know how we'll do without you.
No. See, all that is like not. It's like I had to say it for you guys to say. You know what I mean? It doesn't count.
No, I was gonna say I was just looking for the right
Yo,
chance.
I already said thank you in the chat. John, peep the chat.
Whatever. Okay. All right. So please, guys, you have 1 week. 1 week to do it. All right. If you guys need to meet, no one said anything about office hours today. So I don't know if you guys still want to meet today. If you guys need to meet today, you guys gotta let me know. All right. So we can, if you guys wanted to go over this, I'm not going to take class time to go over the exam. All right. Okay. Hold on. Am I coming through? Are we good?
Yeah, we good. We good over here, man.
Let's get started. We got a lot to cover today. You guys got a quiz on Tuesday. All right. You guys got a quiz on Tuesday. We covered a good amount of it. A good chunk of the quiz is on sequences, what we talked about last class and what you guys talked about in recitation. Identifying the sequence. So if I give you a string of like values like 1, 1/2, 1/4, 1/8, so on and so forth, you should be able to tell me what the general term is. You know what I mean? How it's defined. Where does the end value start? All that stuff. Okay. So that's going to be the first part of the quiz. The next part is finding what a sequence goes to, right? So you taking the limit, showing proper algebra. If you're looking at your midterm, please look at it after class. Okay, focus on this for now. Using L'Hopital's, right? What's the catch for L'Hopital's? How do we use what needs to be true for you to use L'Hopital?
Has to be in an indeterminate form.
Yeah, you need to show indeterminate first in your work. If you just jump straight to the derivatives, I'm not going to mark it right. All right. Using squeeze theorem, Gina talked about that during recitation, right? So it's like you gotta kind of like build sort of quote unquote your sequence and then bound it from the left and the right. And then whatever the left and the right do, if they go to the same thing, the middle has to go to the same thing. Yes, you guys talked about that during recitation, correct?
Correct.
All right, thank you, Jeremy. All right, and then the next part of the quiz is proving convergence and divergence of a series, not a sequence. A series, not a sequence. A series, not a sequence. Okay, they are different things. I said this during last lecture. Okay, we talked about geometric series last class, right? I told you guys you need to have proper justification. What's the justification for a geometric series? 2 things I'm looking for.
Common ratio and
What? I heard common ratio. If a series has a common ratio, is that enough to say it's a geometric series? Okay, remember, so the first thing I'm looking for, is it geometric, right? Does it look like AR to the N, where it has a starting value? Does it look like this? So yeah, you have to identify the A value, you have to identify the R value. That's the first part of it. And the second part is, if, absolute value of R is less than 1, the series converges to A over 1 minus R. I think Gina used C instead, but it's the same thing. It's just the starting value. Or the other one is, if the common ratio is greater than 1, it diverges. You need to show these 2 things to say that a geometric series converges. If I just see you guys, given a series, if I just see you guys jump straight to the equation A over 1 minus R, I'm going to mark it wrong. We can't come to that conclusion until your assumptions are in place. Do you guys get what I'm saying? This is how logic flows, right? You have to state that that you have, in fact, a geometric series. Because believe it, we're going to learn today, there are many other series that exist in this world that are not geometric. This is just a very specific case. So one, you have to state that the series is geometric. Secondly, you have to tell me, is the absolute value of the common ratio less than 1 or is it greater than 1? Then, only then, you can make your conclusion, whether or not the series converges or diverges. And I'm pretty sure Gina went through an example with you guys during recitation yesterday as well, correct?
Correct.
Justifications, guys, are really, really important. Make sure you guys write them in your work, okay? Today, we're going to talk about three more tests with series. Why is this so important? Why do we care about series so much? Well, you saw from Gina's text today that like you're never going to get rid of them. Like as you continue with your calc classes and your engineering classes, they keep coming back. So we need to be familiar with them. But they do have their applications later on. We're going to make the connection between series and functions. What? Yeah, you can actually define functions through series. And it's actually much easier to play with the series, believe it or not, than the functions sometimes. I know, right? Pretty crazy. But in order to do all that, we need to make sure we can tell, is a series going to go off to infinity? Is a series going to converge to a value? Is a series going to just like oscillate between two things, you know? So that's why we need to know how to do all these tests. All right. So we covered one of the tests, geometric series. It's not really a test, but it's like a very specific case, you know, that comes up a lot. But now we're going to go into the tests. I think there's like 7 or so, six or 7, I don't remember. But we're going to try our best to cover 3 today in like 40 minutes. So I don't even think we have time to recap. But the big thing I just want to talk about, right? Sequences versus series. What's the difference between the two? Do you guys remember from last class?
A series is what was it? A sum of sequences?
Very well said. A series is defined as a sum of a sequence. So the terms are all separated by a plus sign, where a sequence is just defined as a string of terms. Yes? The reason why I keep harping on this, the fact that sequences and series are so different, is because the rules for sequences do not overlap with the rules for series. And what I mean is, let's say I take the limit as n goes to infinity of a sequence, right? The result may not equal what a series goes to. Or it could equal, but it may not. So like you cannot use these rules that we're talking about today, divergence test, integral test, direct comparison test. You can't use these rules on sequences, meaning on the quiz on Tuesday, if I see you say divergence test on a sequence, I'm just going to mark you wrong because that's not for sequences, it's for series. So let's see if you were paying attention. Ready? Mohammed, are sequences the same thing as series?
They are not the same thing.
Oh, I thought his first words were they are, and I was like, oh my God. Yes, they are not the same thing, guys. So please don't treat them the same way. Sequences, okay, once again, sequences, we use limits, we use L'Hopital's, you use squeeze, right? Those are okay for sequences. Series, we got to use special tests, okay? All right, so here we go. Let's jump to our first test here. It's called the divergence test. This one's the best one. It's the easiest one. It's the fastest one. This is the first one you run every single time. It's also called the nth term test. Oh crap! I forgot to. Whoops. Okay. What section are we in? I think we're in section 10. I want to say 2. Is it 10.2? I think we're in section 10.2. Yeah, we're on page Linearity with series. We talked about geometric series, some of the geometric series. Okay. Are we in 10.3? We might be. Oh no, we're in 10.2. Okay. Page 570. Here we go. On the PDF. All right, here we go. So what is the divergence test? Once again, this is the first test you run. And honestly, after a while, you can just kind of do this in your head because it's just one, it's just so fast to run. And two, it's like after you do a bunch of these series, you should be able to just like look at one and be like, okay, divergence test doesn't work on that. But we'll get that. Well, we're gonna take it slow, right? So what does the test say? It says if the limit as n goes to infinity of a sub n. So what are we doing here? If the limit of the
Sequence.
oh, thank God, no one said series. If the limit of the sequence is not 0, then you can say, then the sum of the series diverges. That should kind of make sense. Think about it. If I have a sequence that doesn't go to 0, so here, I'll do a quick example with you guys. Ready? If I take the sequence, let's say, I don't know, 1 to the n, and let's say n starts at 1. What does this look like? What does the sequence look like?
1, 1, 1, 1.
Over and over and over and over and over again, right? It's 1, 1, 1, 1. If I take the limit as this sequence goes to infinity, it becomes it's 1. It's going to stay on 1 forever and ever and ever and ever. There's no doubt about that. So since the limit as n goes to infinity of a sub n doesn't equal 0, we can say that the sum of 1 going to 1 to the n as n from 1 to infinity diverges. How do we know? By the divergence test. Boom, done. Think about it, right? What does this series look like? It's 1 plus 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 1 all the way down to infinity. Yeah, it's going to go to infinity eventually. And once again, this is all coming back to what I was saying before here, that even though a sequence might be finite as you go to infinity, the series version may not. And this is why sequences and series are very, very different. Yes? Do we see the point I'm trying to drive into your heads here? Do we have any questions on the divergence test? Pretty easy test, right? One caveat though, I need you guys to write this down. If the divergence test fails, this does not imply, that symbol is imply, by the way, in math. This means imply. You guys know about symbols, right? Because of coding and all that stuff. But this is a handwritten symbol. Like you guys may know this one too. You guys, anyone know this one? No? It's
Oh, I've seen-
Therefore,
yeah, this one's therefore, right? There's this one. This is for all. This is there exists. This means there does not exist. But there's a bunch of shorthands in math. But this one, this arrow thing means imply. So if the divergence, oh, what's up?
Just like which one doesn't mean non-exist? Is it the E with the exclamation point, or is it just
The
exclamation?
exclamation point means not. So E means there exists. This means not. So there does not exist. But whatever, who cares about that, right? If the divergence test fails, this does not imply convergence. Do you guys get what I'm saying? If the divergence test fails, meaning your sequence does go to 0, this does not automatically mean the series converges. It means you need another test. It's inconclusive. Do we understand the difference between inconclusive and like, yes? All right. So, like for example, Here's another quick one. Let's say a sub n is equal to 1 over n, right? So we can't say, so we know if we take the limit as n goes to infinity of 1 over n, it equals 0, right? But because it equals 0, we cannot say that the sum of, whoops, we can't assume that this is convergent by divergence test. This is what I'm saying. You can't go the other way in terms of logic. You have to use a different test because just a spoiler alert, the sum of 1 over n actually diverges. We're going to prove that later on. Okay. So once again, I'm coming back to this idea. The limit went to 0. The series diverged. Yeah. Two very different outcomes. So please, sequences, series, they're worlds apart. You can't do the same thing on them. All right. Any questions on the divergence test? And this probably explains why divergence test is so fast, right? It's like probably most of the time the divergence test will fail, only because like divergence test problems are super fast, right? And they're gonna give you like harder problems to do. So we gotta build up our tool belt here and move on to another test. We gotta learn some other tests here. I'm gonna move on to what's called the integral test. This is the next test. So far we've done geometric series. We talked about divergence test. The next one is the integral test. All right, integral test. Well, use your context clues. What do you guys think this one's going to involve?
Oh, I don't know.
Integrals.
Maybe,
Yes.
Integrals.
Yes, integrals. It's going to involve integrals. All right. However, before I do this, I'm going to show you guys. So like, I need to go through this quick aside here. You guys need to understand this sort of logic for the integral test to kind of make sense. Ready? So we're going to pause on the integral test real quick. This aside will also explain the one after the integral test, DCT. If you understand this aside, integral test will make sense. DCT will make sense. The direct comparison test will make sense. Okay. So watch. Here we go. Ready? So two scenarios. Ready? So first one is, let's say I have a function that looks like this. Let's call this f of x. Give you guys a second. I see some of you guys are still ready. So let's say in my first scenario, this is, I'll call this scenario 1. I have a function, right? And I want to take the area of this function from 1 all the way down to infinity, which means I'm going to need what if I were to integrate this?
a limit.
Okay, we are going to need limits, but we're going to need, starts with I. And this is why all you got this question wrong. Improper integrals. We needed improper integrals for this, right? Because it's going to a place that we're not allowed to go to, quote unquote. You know, that was one of the questions on the midterm. No one used limits. Maybe one person used limits, I think. But most of you guys missed the improper integration problem completely. Anyways, so if I want to take the integral of this red function from 1 to infinity, right? And let's say this diverges. What does that mean again? If I have an area that's divergent, what does that imply?
That it goes into
infinity. Thank you.
Yeah.
The area just grows too big for us to use a finite value to it. We can draw one and only one conclusion about a function above. Let's say I have a function above and I'm going from the same bound. I'm doing the same thing. Do I need to do the work for blue? Do I need to set up the integral? Do I need to put the function in? Do I need to blah, 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 and get to a final conclusion?
No, you don't need to do that stuff.
Okay, why?
Because it's a similar function to the red one, so it's just the same thing.
Similar how?
Well, it's the same shape, right?
It's different by a constant.
That's not the
Is
same
that
shape,
one?
no? Wait, what?
That's like, so the other one was supposed to be parallel, and now this one's not.
Parallel. No, we're not talking about, we're not really talking about parallel. What's the difference
it's
between the blue and the
greater
red?
It's greater than the red.
Thank you. Think about it, guys. If the red is too big, then that means anything that's above will,
Also be too big.
Diverge.
oh God. All right, yes, right? This means anything that falls above the red, this is, by the way, guys, this is how logic works, right? Save yourself the time. You don't have to do the work for the blue function. Doesn't matter what the blue function is, so long as it fits on the bounds, the same bounds, and for all of those values, it falls greater than the given function. But this means, this implies that we need to know this. We need to know that the red one diverges first. You know what I mean? Before we make any conclusions of the stuff above. Does that make sense? Last part is, what would happen if I had an h of x that fell under? What can you tell me about the green area? These are all going to infinity, but what can you tell me about the green area?
It'll be smaller than the red area.
Keep going with that logic. Therefore,
It diverges.
It might converge.
in math, we don't like that word. Might, could, maybe.
It
We don't-
conditionally converges?
You're using words that you don't know how to use yet.
No, I don't, but it sounded familiar.
That's later on. We'll talk about conditional convergence later on. Guys, just think like logically, right? Be Spock for a second, right? If you have something that diverges, right? That means it grows too big. But what happens if you have something that falls under it? Do we know anything about it? Can we draw conclusions with the given information? With if we knew that red diverges?
No,
It
we
doesn't
can't.
grow too big.
We don't know that, Daniel.
We
Guys,
can't
the
make a
answer is you don't know.
Logically, it's inconclusive.
So we say, so we're gonna say that green is inconclusive. Do you get what I'm saying? Like, you can't say like, it looks like it converges. I guess you could say that, but that is not an answer that we can use, right? That's like a gray area. We in math, we like black or white. We like it comes to an answer, it doesn't come to an answer. You know what I mean? Green is inconclusive. But once again, this is all based off of our assumption. He wrote S. Yeah. Okay. This is only based off of the assumption that the red area diverges. Does that make sense? Once again, so if I have something that's divergent, everything above is divergent, everything below is convergent. Do we understand this logic? I'm sorry, everything below is inconclusive. Oh my gosh, I messed that up. Yeah? That's the first scenario. The second scenario. Ready? So we're going to talk about this red area again, but now this time, red area is convergent, and we know this. This is our assumption. We're going to do the same thing. We're going to look at the case above. We're going to look at the case below. What can you guys tell me about the case below? Think about it. If I have something that eventually goes to a finite number, meaning it smushes down, it compresses down enough to hit a finite thing. What is anything that falls below that? What can we assume?
Anything below it must also converge.
Why?
Because it's gonna like convert
kinda
to a
like-
finite value also. It has to. I mean, there's no
Okay.
there's no increased like slope for them to for it to keep it like
Well,
incrementally increasing.
If
Right,
if
like-
the one above it is measurable, then the one below it should be measurable as well. Right?
I mean, to me, it's just like it's the opposite of the first one. Like if we know like in the first one, we know that that's too big to like be quantified, and we know anything bigger than that must also be too big. Then if we know like this can be quantified because of how small it is, anything smaller than it also can be like quantified.
Yeah, basically. Good
Are we
job.
right or
Good job,
completely
Marco.
wrong?
So yeah, I mean, I'll be honest, you guys, I get it. It's because you guys don't use logic enough in your real life that You know. I'm just saying, because I asked why, and you guys just like, I can sum up your answers in this one phrase, because it is. Like that's what you guys basically just told me, because it is. But like, all right, whatever. It's okay. It's okay. It's all right, whatever. So yes, anything that's below will also converge as well. Why? Look at the growth rate. Look at how it's behaving, right? This wouldn't be true if like the green like suddenly did that. Do you guys get what I'm saying? It never dips above. It always stays below. That's actually going to be real important for the integral test.
That's what I said.
I don't remember you saying anything about growth rates, but okay, sure. So we can say that green converges also. We don't have to do a test for it. We don't have to do a thing for it. We know that green will converge. And then here we go. We're going to go to the other side now. What can you tell me about stuff that falls above?
Inconclusive.
Good. Okay. I'm not gonna ask why this time, but good. All right, yeah, blue is gonna be inconclusive, right? Because like, think about it, right? If red could like possibly be like the tipping point, you know what I mean? Between convergence and divergence, right? If blue is like just above red, who knows? That could be just enough for it to blow up to infinity. You guys get what I'm saying? We don't know. It's inconclusive. It's blah, 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 blah. Do we have any questions on this idea? This is I'm kind of going out of order. This is actually kind of how DCT works. This is like sort of DCT, okay? But this is like a very big idea that's going to come in a lot of these tests that we do. But do we understand these two pictures? Questions, comments, concerns? Great. All right, integral test. I'm running out of time. Integral test. There are some assumptions that need to be true for you to run integral test. Just like geometric series, right? The series has to be geometric. Common ratio has to be less than 1. Then and only then can you say convergence, right? Integral test, there are 3 things that need to be true. Ready? Here we go. So it states that, we lost someone. It states if you have a function that is positive, continuous, oh shoot, continuous and decreasing. Positive, continuous, and decreasing. That resembles a given, I'm going to use that term loosely, that resembles a given sequence if you have a function that is positive, continuous, and decreasing that resembles a given sequence. And I'm going to call it like f of n from, oh, f of x, sorry. F of x for x is greater than or equal to 1. Hold on, wait. If you have a function that is positive, continuous, and decreasing that resembles a given sequence f of x for all n greater than or equal to 1, then if what? I did not write this correctly in my notes. Hold on, let me look at the thing in my book. I think this is 10.3. Wow, yeah, okay. Yeah, then if integral of 1 to infinity of f of x dx converges, then sum of n equals 1 to infinity converges. 1 to infinity of f of x dx diverges. Then from 1 to infinity, a sub n diverges. Very wordy, I know. This isn't even like the proper phrasing and stuff, But basically what is it saying? It's saying if you create a function that resembles your series, and so long as if that function is positive, continuous, and decreasing, when you take the integral of that function from 1 to infinity, or whatever the end bounds are, whatever happens to the function will happen to the series. If the function is convergent, the series converges. If the function is divergent, the series diverges. Does that make sense? So essentially, what are we doing here? We're using improper integrals on a function that closely resembles the series, or I guess the sequence, right? And we're letting that go to infinity. And we're letting the conclusion of the integral tell us what is going on with this series. Does this make sense? Maybe. Let me show you guys an example. Here we go. All right, did you guys get this down? Anyone still need it? Okay, so let's call this example 1. The one that I started before, 1 over n. I already told you guys the answer to this one. It's divergent, right? But let's prove it. Let's use the integral test on this. All right, so here we go. Ready? So 1 over n, I'm going to show you guys also pictorially why this makes sense, right? But 1 over n, we're going to say that this closely resembles 1 over x for x is greater than or equal to 1. And then on top of that, please note what I'm about to do, because you need to do this in your work too. This is positive, continuous, and decreasing. Yes, that's fine. That's enough. You don't have to prove positive. You don't have to prove continuous. You don't have to prove decreasing. You just need to state it on the interval that's given, right? We know this. We know what 1 over x looks like, right? It looks like, oops, it looks like this. Yes. And from 1 to infinity, which is the bounds here to infinity, this is going to closely resemble our series, right? So if the black represents the area under the curve, right? I'll do this in green, right? If this is 1, this represents from 1 to 2, the height is going to be 1, right? From 2 to 3, the height is going to be 1/2, and then 1/3, and so on and so forth. Do you guys see the comparison that we're doing here? Yeah. So because it's positive, continuous, and decreasing, we can say that the integral under this curve can give us can tell us some stuff about this series. And once again, this is going back to what we were just talking about, right? The blocks, are they above or are they below?
Above.
They're above. So what are we hoping that the area is going to be?
Wait,
Like overestimated.
converging so that we can say the one below is converging.
Okay, let me go back. Let me go back to the pictures. Okay, here we go. Ready? In the second case was the convergent case, right? Red was convergent, so we only knew stuff that was
Below.
Below it.
below it. The first case, red was divergent, so that means we only know stuff
Above it.
above it. Everything below is inconclusive, right? So once again, let me go back to the picture. The green is above. So we want the area under to be
Divergent.
divergent. That's the only way we're gonna get a conclusive statement. Do you guys get what I'm saying? Like this is what we're trying to prove, what we're trying to figure out, right? We're trying to figure out, does this thing converge? Do the blocks converge or do the blocks diverge? We don't know. So we have to use what we can find out, hence the area, to conclude that for us. Yes? So here we go, let's do it. We're hoping that the area of this from 1 to infinity is divergent. Let's prove it. Well, what is the integral of 1 over x?
ln of absolute value of x.
Thank you for saying absolute value. And I need a plus c, right?
It's bounded.
Thank you. So Dan's paying attention. We're going from 1 to r, taking the limit as r goes to infinity, because this is an improper integral and I need my limits on every single step. I'm not salty. I'm not salty. And then we plug in the upper bound minus the lower bound. So it goes limit as r goes to infinity, ln of absolute value of r. And then ln of 1 is just 0. So that's just going to go away. It's going to be minus 0. What's going to happen when this goes to infinity? Do you guys know what the graph of ln looks like?
Not off the top of my head.
I just gave it to you. I just gave it to you. It's right on the screen.
Okay,
What is that graph going to?
Infinity.
It's going to infinity. This is divergence. What did we just prove here? We just proved that we know that the black is divergent. Therefore,
Anything above it also diverges.
okay, therefore we can say,
The series of 1 over n diverges.
and how did we know that? What test did we just use?
The integral test.
Okay, you see, do you guys see? You need all of that. You cannot just say it's divergent. That's a big shame. That's a big no-no, okay? You need to say the function is positive, continuous, decreasing, because if it's not those things, right? Once again, that black could have like dipped above the green and it would have been inconclusive, you know? It needs to be positive, continuous, decreasing for the whole interval. That's so important. You need to show the integral step. You need to show what the final outcome is, right? Is it convergent or divergent? Then you say your final statement. Therefore, or you can do the 3-dot thing if you don't want to write out therefore, the sum of 1 over n from 1 to infinity is divergent. How do we know? By the integral test, which uses, so this is important too, right? Which uses this and this together. Once again, you cannot say it's divergent. That's not enough. You need proper justification. You need the stuff that leads up to your conclusion for your answer to make sense, to be acceptable. Do we have any questions on this? On the write-up? Does it have to look exactly like this? No. Do you need a picture? No. The picture was just to help you. Yeah. Let's do one more example because I don't think I'm getting to DCT today. I'll probably get to DCT by Monday. So let's call this example 2. N equals 1 to infinity. So this is our second example. All right. What do you guys think? Do you guys think this one's going to converge or this one's going to diverge also, like 1 over n? Just a guess. Just guess. I'm not looking for the right answer.
It's gonna diverge.
You think it's going to diverge?
It's gonna converge.
You say it's going to converge? Well, let's use the integral test. Why can I use the integral test? Let's see if you've been paying attention.
Because it's positive,
positive,
continuous, and
it's
decreasing.
decreasing and continuous.
I'm telling you guys, if you say it out loud, you'll remember it better, okay? This closely resembles, I shouldn't use that, I'm sorry. I should say resembles f of x, which is equal to 1 over x squared. And 1 over x squared is, in fact, it is positive, continuous, and decreasing on x is greater than or equal to 1. You need to say this in your write-ups. The next step, we just integrate it. That's it. We integrate this from 1 to infinity. How do we integrate 1 over x squared or x to the negative 2?
-1/2 x to the negative first.
You want to try that again?
You take the limit.
Okay, well, we're gonna need a limit, sure. But the integration step. It's x to the negative 2, guys. So we add 1 to the exponent.
It's negative x to the negative 1.
Yeah. And we're going
Yeah,
from
my
1
bad.
to r. It's okay. What do you guys see? What's gonna happen here? If I plug in r, I get negative x, I'm sorry, negative r to the negative 1. We're taking that to go to infinity. Minus negative 1, sorry, to the negative 1. Upper minus lower, right? What's going to happen to that first term as it goes to infinity?
Gonna go to 0.
It's going to go to 0, right? This is the same thing as negative 1 over r. Limit as r goes to infinity, right? So this is going to go to 0 plus 1. We get 1. So we found a conclusion with our area. Our area was convergent, right? I'm going to draw the picture again. This is where I lose people usually. So just please pay attention here. Ready? I'm going to do a trick. And you guys are going to be like, that's cheating. But just give me a second to explain it, okay? Ready? Here we go. This is 1 over n squared. It looks like 1 over n squared, right? We just said everything under the curve goes out to infinity. And we have concluded that this is convergent. Our series, for our series though, we're gonna line this up a little differently, okay? Just bear with me here, okay? If I do this, this is the same thing as, I don't know why it's in blue, sorry. This is the same thing as 1 plus n equals 2 to infinity, 1 over n squared. All I did was I'm just disregarding the first term. You with me here? Yes? So that means that one block, if this is one, that one block, it's like out here off to the side. I'm just like disregarding it. And I'm taking everything else and putting it under. So this is the 1/2. This is the next one. This is the next one. So on and so forth. Why am I doing this? Why am I?
So
Because
that it
now,
falls under.
Wait, what?
So that it falls under.
So that it falls under. Why is that so important?
Because then we know it converges.
Because then
If
you
the
can
above
make
is converging.
then you can make a conclusive statement. Guys, remember, I know it's a little confusing, right? The black sum, the black area is convergent. So if I included that first piece, it would have been an inconclusive picture. Everything would have fell above. You wouldn't be able to say a conclusive statement about the, I don't know why I changed the color, but the blue and green blocks. Do you get what I'm saying? So I kind of moved the first piece out so that everything was under, because something that converges plus something that's convergent is
Something that
that
converges.
converges.
Does that make sense?
Yeah, I mean that makes. I like.
Wait,
that.
hold on, wait, John, that's really confusing because on that last example, wait, why didn't we pull out the block in the first place like last time? Why didn't we do that for the last one?
Because we can
Because the rest
measure
of them were
stuff
over.
that's more, yeah.
What?
We can measure stuff that's over when it's divergent.
Yes, hallelujah, you guys got it. Yes, do you guys see, right? And do you guys see why I had to do this picture first, okay? This picture explains integral test, all right? Oh man, that works so well. All right, any questions on this? So it's like you have to pay attention to your assumptions. You have to pay attention to what you know. In this, so the second example, right? Where is it? Where did I write it? I know I wrote it somewhere. Oh, here we go. Yeah, the second example, we knew that the area was convergent, so we had to do that shift thing. Do you have to do this in your work? No. I'm just showing you both cases with the one divergent case, one convergent case. Okay, and I'm showing you why the results of the integral test at these two pieces, I'm showing you why these two work. That if the integral is convergent, it'll show that the series is convergent, or if the integral is divergent, the series diverges. That's all I'm doing. I'm just showing you the guys why it works. But now you guys know, now that you guys know, we can get to our final statement here, right? For number 2, because we're not done yet. We didn't answer the question. We didn't say if the series is convergent or divergent yet. So what am I going to do? How do I write my final statement here? This is just side work, but how do I write my final statement? We just found that the integral converges. We just found that it's 1. So
Therefore, the sum of this series is convergent by the integral test.
you can shorthand. I don't care if you use symbols. You can say conv and dive. That's fine. I don't care about that. You can use DCT instead of direct comparison test. You can use INT instead of integral test. You know, that's fine. You do not need a picture for integral test every time. I was just doing that to show you guys why this works. Cool. Questions on the integral test? Let me tell you a caveat about the integral test. Ready? Here's the trick to integral test. You guys ready? Integral test, this is one of the more longer tests. It takes a little bit more elbow grease. That's why think about this whenever you're given a series. If the sequence looks integratable, use integral test. Works 95%, 99% of the time, okay? In this class. If you have a sequence that looks integratable, you're gonna use the integral test. So for example, like if I have, excuse me, something like, no, not that one. Let's do, I'm looking for something on your homework that, here we go. Actually, no, that one is also, what is a DCT? Ooh. Ready? Ready? So if I have something like this. What do you guys think? This closely resembles f of x is equal to 1 over x ln of x 3/2. What do you guys think? If I were to integrate this, what would I need to do?
Integration by parts.
No. Nice try. Swing and a miss. No, we don't see it. This is a very common one, actually. No. It's a U sub. Do you guys see the U sub? If I let u equal to ln of x, what's the derivative of u?
1 over x. Yep.
And we have a 1 over x. You guys see that? So this is what I mean. If it looks like you can use u sub, if it looks like you can do integration by parts, if it looks like you can do partial fractions, trig sub, all these methods that we learned, yeah, you're gonna do. It's probably gonna be an integral test one. Is that okay? Do you guys get what I'm saying? I'm just gonna dot this. Yeah. I couldn't get to DCT, unfortunately, but Monday we'll probably do DCT along with maybe the next one after that, and possibly go over some stuff for the quiz just to make sure you guys are good. I might, you know what? I want to make sure that you guys are exposed to it early. I'm gonna make a video for this lecture. I'm just gonna go through DCT. If you guys, once again, if you guys understand, hold on, this thing, if you guys understand this thing, DCT makes a lot of sense, okay? It's like, you gotta start with a series that you know, and then it's like, you're gonna either try to fit the one that you're trying to figure out above or below, depending on the one that you know, but it follows this idea. All right, so I'm gonna make a video. I need you guys to check out that video, and so that on Monday we can kind of talk about it. Sound good? All right. Any questions though on the stuff that we did today with the integral test? No? Any questions about the quiz coming up or the homeworks or anything like that? No? Anyone want to schedule coming to an office hours today or no?
Can I let you know on GroupMe if I'm coming?
Please and thank you. Let me know. All right, guys.